Hello. In this series, we will revisit the classical exact solution techniques used to solve second-order ordinary differential equations. The nominal form for a second-order differential equation has this form. You can see that the highest derivative here is second-order derivative, and that's why we call this as a second-order linear ODE. K0, K1, K2 are the coefficients of this differential equation, and ft is the right-hand side, t is the independent variable, y is the dependent variable, and our mission is to find an exact solution or expression for y of t. Similar to first-order ODEs, the solution has two parts, a homogeneous part and a particular part. Let's see how to solve for each of them. So for the homogeneous part, this is the part of the solution that makes the differential equation equal to 0. And if we reflect on this equation, you see that you have a function y of h. When you add it to a scaled version of its derivative and add both to a scaled version of the second derivative, you're going to 0. So this suggests that both y, the derivative of y, and the second derivative of y should have the same function anatomy, such that when we add them together, we can get rid of them. This property is happening in exponentials because derivative of exponentials are also exponentials of the same exponent, and then we can add them together using some scaling factor to get a result of 0. So this suggests that the homogeneous solution would be in the form of an exponential function. So in order for us to generate that homogeneous solution, we construct what we call the characteristic polynomial. To construct the characteristic polynomial, we replace the derivative operator by some variable s. So the second derivative here will be replaced by s squared. This first derivative here would be replaced by s, and if no derivative, it would be s to power 0, which is equal to 1. Okay, this gives us what we have here, what we call as the characteristic polynomial. The roots of this characteristic polynomial determine the possible solution for the homogeneous solution. So we have the characteristic polynomial, which for a second-order differential equation is a second-order polynomial. So second-order polynomial has two roots that can be obtained using this nominal equation. Now, since we have two roots, we have multiple possibilities on the shape of these two roots. Option number 1, we might have two unique real roots. If this is the case, then the homogeneous solution would be 2 exponential, one whose exponent is the first root, the second is an exponential whose exponent is the second root. K1 and K2 are some constants that can be obtained using the initial conditions of the differential equation. The second possibility of the root is that we get two identical roots, meaning that alpha 1 and alpha 2 are both equal to alpha. The homogeneous solution still be an exponential function whose exponent is alpha, because alpha 1 is equal to alpha 2, which is equal to some real number alpha. But now we have this extra t here. The third and last possibility for our two roots is that they are both unique, but they are complex conjugate. Okay, so the two roots are complex conjugate with a real part alpha and an imaginary part beta. So in this situation, the homogeneous solution would be sinusoid function with an exponential envelope. The exponential envelope has an exponent alpha, which is the real part, and the sinusoid are oscillating at a frequency beta, which is the imaginary part of our roots. So knowing the roots of the characteristic polynomial would guide us to one of three possibilities for the solution of the homogeneous part. Each possibility has constant k1 and k2, which can be obtained using the initial condition, as we are going to see in the next video. The second part of the solution is the particular solution. The particular solution is the solution that makes the differential equation give us the right-hand side, which is equal to ft. Similar to the first order ODEs, we usually have the particular solution in a similar form to f of t. So we have the same table from last time. Given the nature of ft, we can hypothesize a possible solution for the particular solution. You can see that the particular solution has some unknowns. We can use that proposed solution substituted into the differential equation in order for us to solve for those unknowns. So if the differential equation is given as k2 y double prime plus k1 y prime plus k node y equals to f of t, all what I need to do to solve for those unknowns in the proposed solution is that I plug in that expression into this differential equation, and this will give me equation to solve for those unknowns. We are going to solve an example in the next video to reinforce the methodology to compute those parameters. So in conclusion, we have seen the nominal form for second order differential equation. The highest derivative in the differential equation is the second derivative, and the solution is also composed of two parts, homogeneous part and particular part. The homogeneous part is one of three options depending on the roots of the characteristic polynomial. Thank you.